Welcome back to Lecture 10 of Robot Dynamics. After an introduction to rotorcrafts and the modeling and control of a quadrotor in segment 1 and 2, we will now in segment 3 focus on the thrust force generated by propellers and rotors. Rotors and propellers are the elements which allow us to generate forces which act on the rotorcraft to control it in free space. We have typically different forces which are acting. First, we have the thrust force. This is the main force which generates typically the uplift to keep the helicopter in the air at a certain position. Additionally, we have the drag torque, which is actually the torque which is resisting against the rotation of the rotor. This is then also directly linked with the power the motor has to deliver to generate the thrust force. Additionally, if we have a forward speed, we have the hub force, which is orthogonal to the thrust force, and the rolling torque, which is additionally acting on your rotor if you have a forward speed. Similar to blade elements of a wing, the thrust force and also the thrust torque are typically in a first order approximation directly proportional to the rotational speed of the rotor. They are actually then also dependent on the density of the air, the surface which the rotor covers during its rotation, and a thrust or drag constant which is representative of the type of propeller you're using. These constants are additionally dependent on the pitch angle of the propeller, the Reynolds number, the propeller speed, velocity, and rotational speed. If the rotor is moving forward, meaning that it's not stationary, you will have an imbalance in the forces, as you can see it on the drawing in position 1 and 2. So at one point the rotor is actually moving towards the direction of speed, and at the other end it's moving away from it. These movement actually generate the hub force, which is opposed to the horizontal flight direction, but is also proportional to the square of the rotational speed, and then the roll moment, which is again proportional to the square of the rotational speed. The two constants for the hub and rolling moment are mainly dependent on the advance ratio, which means on the ratio between the with forward speed and the rotational speed of the propeller. In the first step, we are now calculating the thrust force based on an ideal propeller. This can be done by using the momentum theory, which says that the power put into the fluid to change its momentum is then equal to the thrust force. For doing so, we have to take a couple of assumptions, which are typically well satisfied in a context of a rotorcraft. So first of all, we assume that the propeller disc is infinitely thin. Furthermore, we assume that the thrust and velocity distribution is uniform over the disc, so we can use and look at the one-dimensional flow analysis. Furthermore, we assume quasi-static airflow, so the flow properties do not change over time. And last and not least, we assume that we have no viscous effect, so the profile generates no drag, and the air is incompressible. As you might recall from fluid dynamics, the momentum theory consists of three main equations. The first one is called the conservation of fluid mass, which means the mass flow inside and outside a controlled volume must be equal in a quasi-static flow. And this is represented by the integral of the density multiplied by the flow speed and integrated over the whole surface in the normal vector. The The second equation is the conservation of fluid momentum, which says that the net force on the fluid is the change of momentum of the fluid. So this means the force in equation 2 is equal to the integral of the pressure over the surface and plus the density multiplied by the flow speed square in the normal direction at the surface. The third equation is the conservation of energy, which means that the work done on the fluid results in a gain of kinetic energy. So in this equation we have on one side the integral over the kinetic energy multiplied by the flow through the surface is equal to the power of the system. Let us now consider a typical flow feed around the propeller as depicted on the right side of the slides. In this flow field we define 4 different control surfaces. Surface 0 is the inflow part, which is far away from the propeller. Control surface 2 and 3 are just above and below the propeller, and the control surface 3 is then at the outflow end of the whole flow through the propeller. Now for each of these flow surfaces we have typically a speed, which is defined, a surface area and the pressure. Now if we apply the conservation of mass which we have just been before, which is the integral of the density multiplied by the speed and integrated over the surface, we can actually for each control surface calculate this conservation of mass. This is then shown in equation 4, where the integral is directly the multiplication with the surface if we assume, as we have defined before, that the flow field is constant over the whole surface. Now from equation 4 we can directly deviate also that U1 is equal U2. So this means that we have no change in speed through the disk, but of course we will have a change in pressure, which is then directly reflected also in the thrust force generated by the propeller. As a next step, we can now apply equation 2 and 3 of the momentum theory to our flow around the rotor. The second equation is the conservation of momentum, which says that the force on the fluid is the change of the momentum in the fluid, which is given by the equation 2 we have just seen before. So we need the integral over the pressure at the whole surface of the fluid, which we see on the left, and the integral of the speed, the surface speed in square, in the normal direction of the fluid. Now we know that the surface outside is actually all ambient pressure, so the integral of the pressure over the surface is 0. So this simplifies our equation to an equation where the thrust is directly calculated by the integral of the inflowing speed multiplied by the density and integrated to the surface plus the outflow speed in square multiplied by the density and integrated over the surface. Again, if we assume that we have a constant speed distribution over the whole surface, this boils down directly by multiplication of the surface area, and so the thrust force can then be simply calculated by using also equation 4 and 5 from the previous slide as the density multiplied by the rotor cross-section area and multiplied by the speed v plus u1 multiplied by u3. So this is the next element for getting a more detailed description of the generation of forces or thrust force in a flow. So the last equation of the momentum theory is the conservation of energy, which defines that the work done on the fluid results in the gain of kinetic energy, as we can see here in the equation 3, which is also from previous slide. Now for the power, we can actually calculate this by the multiplication of the force by the speed at the rotor surface. And this is then equal to the integral over the cube of the surface, the speed of the fluid through the surface, and the difference between the inlet and the outlet of the whole system. So again, if you use then equation 4 and 5 of the previous slides, we can get an expression which is now defined as equation 7, where the thrust power of this rotor system defined by the momentum theory is equal to 1/2 of the density multiplied by the rotor surface and multiplied by different elements of the speeds which are defined at the different levels of this control fluid blocks. If we now combine equations 6 and 7, we can see that the difference in the outlet speed, U3, is equal to twice the difference in the speed just above the rotor, U1. Furthermore, we can see that the thrust force is proportional to the surface area at the rotor multiplied by the density and multiplied by the difference U1 of the speed above the rotor and multiplied by the absolute speed above the rotor, which is V, big capital V plus U1. Furthermore, in hover, we can assume that the inlet speed V is 0. This means that equation 9 is further reduced, and we directly see for the thrust that it's equal to twice the density multiplied by the surface area at the rotor and multiplied by the speed in square at the rotor. This looks familiar. Again, we have a relation which is squared the speed, which is typically standard in aerodynamics. Furthermore, we can assume that the inlet surface is going to fit infinity, which intuitively is clear that we have a very high inflow surface. If we assume this, we can then directly calculate that the outlet surface A3 is half the surface at the rotor disc. In general, we know that the power is the force multiplied by speed. Now, in our specific case of the rotorcraft, the power of the rotor is equal to the thrust force generated by the rotor multiplied by the speed at the rotor. Now, if we combine this with equation 10, which we have seen just in the slide before, we can find an equation for the power in the hover case, which is equal the thrust force to the power of 3 divided by 2 and divided by the surface area at the rotor. Now, if we assume that the rotorcraft has to carry its own load, which is mass multiplied by g, we can actually find an equation of the power for hover. Now, what does this mean? This means that the power depends on the disk load, which is defined by the thrust force divided by the surface area. So with a decreasing load, we have reduced power, which means that we should have for a given thrust force a surface area as big as possible. But of course, you have some mechanical constraints. The bigger the propeller comes, the closer you are getting at max speed at the tip of the propeller. On the other side, this is the reason why standard helicopters, big human-carrying helicopters, are getting close to the Mach speed at the tip of the helicopter. Additionally, of course, you are limited by the surface, the profile structure and the drag, and there is some additional influences, and of course also at the length of the tail. The bigger the rotor diameter comes, the more bulky the whole helicopter will be. The thrust force we just calculated using the momentum theory is of course an ideal thrust force. This allows us to actually define the figure of merit. The figure of merit is equal to the ideal power required to hover divided by the actual power required to hover. The ideal power required to hover is exactly what we can calculate using the momentum theory, and the actual power is what we probably measure in the rotorcraft, or we estimate by using a more appropriate and more detailed model of the helicopter. So the actual power includes also profile, drag, blade tip vertices, and a lot of additional effect. So the figure of merit typically allows you to compare different propellers with the same disk load and allows you to select the most appropriate one for your application case. In order to get a better estimate of the thrust force, you combine momentum theory with blade element theory. In blade element theory, you cut down the whole rotor in small blade elements, and then you analyze this by making a calculation of the lift and drag force for each element in the rotor, and you sum up this over the whole diameter of the rotor. The lift and drag forces acting on a blade element of a rotor can be calculated similarly to the forces acting on a wing of a fixed-wing airplane. With the relative airflow V, we can determine the angle of attack and Reynolds number of the blade element. The corresponding lift and drag coefficients can be then found on polar curves for blade shapes. We'll see an example in the next slides. V, the airflow, is composed of Vt, which is the rotational speed of the rotor, multiplied by the radius at the blade element, and the axial velocity, which is composed of the main element of the axial velocity and the induced velocity. The main component of the axial velocity can be calculated with the help of momentum theory, as we have seen before, and the induced velocity is based and influenced by the profile. On this slide you can see an example of the lift and drag coefficient of a certain propeller blade as a function of the angle of attack. On the left side you see the lift coefficient as a function of the angle of attack. You can see that the lift coefficient will raise with the angle of attack, but at one point you will have a stall and the lift coefficient is drastically dropping. On the other side you can see that for example for a lift coefficient of 40 you have a drag coefficient which is probably about 10 times smaller, which means that your propeller is pretty efficient and is mainly generating lift and very little drag. Here is another representation of lift and drag as a function of different angle of attacks with different colors. And you can see again that the lift coefficient is much higher than the drag coefficient, which is actually what you want, because you want to mainly generate lift and as little drag, because the drag is directly converted into the propeller power. If you want to fly very dynamic maneuvers with a quad rotor or any other rotorcraft, you might also consider the dynamics of the motor. A DC motor is typically composed of a mechanical and electrical system. The mechanical system can be modeled as any other mechanical dynamic system, which is in the case of the motor, the inertia multiplied by the derivative of the rotational speed is equal to all forces acting on the motor. In the case of the rotor, the forces acting on the motor are on one side the motor torque, which generated by the motor, and on the other side the load, which is the force, which is the counterforce actually from the propeller. The generated torque due to electromagnetic field in the coil is typically calculated by the current multiplied by the torque constant, and the torque constant is dependent on the motor and typically given by the manufacturer. The electrical system is a typical voltage balance, so you have the inductance multiplied by the derivative of the current in the coil is equal to the voltage in the coil minus the resistance multiplied by the current and minus the induced voltage. Induced voltage due to back EMF of the rotational static magnet are typically also a constant multiplied by the rotational speed of the rotor. With this system you can actually consider a rotor, but in most cases the electrical part of the motor is much faster and you only have to consider the mechanical dynamics of the motor in your system. With this, the lecture 10 ends. I hope we have been able to show you how typical rotorcrafts are built and designed, but especially also show how we can model in a typical example of a quad-rotor rotorcraft the system, how we can define an appropriate control, and how we can estimate the torques and forces of the propeller, which are then acting on our rotorcraft. Thanks very much for your attention.